So we're going to look at a specialized use of the reverse chain rule, which allows us to get integrals which are equal to logs. Exciting, let's go. So as I've noted before, integration and differentiation, they're just opposites of each other. If you know that something differentiates to y, then you know y will integrate back to what you started with. And we're going to apply that here to this shortcut that we had for the chain rule. If we differentiate ln of fx, and then we get ourselves a fraction with fx on the bottom and its differential on the top. And what that means is the reverse must obviously be true. We can integrate and go back the other way. So said more formally, if we are integrating a fraction where the top of the fraction is equal to the differential of the bottom of the fraction, then we get ln of fx, and obviously plus c. So let's have a look at some basic applications here. All we're doing is whenever you see that you have to integrate a fraction, just have a look to see if the top and the bottom differentiate into each other. So what could we say here? Well, if fx was equal to 3x squared minus 5, which is what's on the bottom of this fraction, then the differential of that would be 6x. Yeah, exactly. So the bottom of this fraction and the top of this fraction works out perfectly. So we know this is just going to integrate to the logarithm of fx, so ln of 3x squared minus 5. Fair enough. What about this second one? Well, again, we'll consider the bottom of the fraction to be fx, 3 plus sine x. Then we'll differentiate it. 3 goes away, sine x goes to cos x. Remember, we're talking differentiation here. And yeah, that works out exactly because the top of our fraction is f dash x and the bottom is fx. So that's going to be ln of 3 plus sine x plus c. So again here we've got a fraction, we've got e to the 4x minus 7 on the bottom, so we'll consider that to be our fx. And if we differentiate that, well, you can use a little shortcut for it, but you can also use long chain rule. We'll get 4e to the 4x. So what we want at the end of all this is to integrate e to the 4x minus 7 over 4e to the 4x, because we know what that's going to go to. We know that's going to just go to ln of the bottom. But that isn't the same as what we've started with here, you know? So we need to think, well, how could we make this into the same fraction? And what we're going to do is we're going to say, well, okay, yeah, we could have 4e to the 4x here and e to the 4x minus 7 if we also times the top by a quarter, because then the top of that fraction would be a quarter of 4, would just cancel out. And so e to the 4x is the same as a quarter of 4 e to the 4x. Now we said that any constant with an integral you can take and put at the front of it. So we're going to put our quarter there. And now you can see that that's a chain that works. E to the 4x over e to the 4x minus 7 is a quarter of 4e to the 4x over e to the 4x minus 7. And then we can take the quarter and stick it at the front. And now the important thing is that this is our fx over f dash x over fx, because those are the values that we found right at the start. So we can go to our answer being a quarter of ln of the bottom of the fraction of e to the 4x minus 7 and then plus c. So if it's not quite the same, you kind of have to fiddle around with the numbers to make the top of the fraction be the differential of the bottom. So here's another example. I've got 7 cos 2x. I've got 2 sin x cos x on the top. So what's the point with this one? Well, we'd actually have to use a little bit of a trig identity to start with, wouldn't we? We'd have to spot that 2 sin x cos x is the same as sin 2x. So you can get your trig identities in here as well. And then let's have a think. So we've got fx on the bottom is equal to 7 cos 2x. And what's the differential of that? It's going to be minus 14 sin 2x. Now you might want to do some chain rule to convince yourself of that. So this is what we want the bottom and the top to look like. Obviously the bottom does look like 7 cos 2x, but we want the top, again let's include a little bit of a step in between, to look like minus 14 sine 2x. Doesn't at the moment though, so how can we do that? Well, again, we'll take out a factor. So we want this to be minus 14 sine 2x. And that means that we're going to need to take out a factor of minus a 14th on the top. And then that's a chain that works, because sine 2x is equal to minus a 14th of minus 14 sine 2x. And then we can take out that minus 14th and stick it at the front. So we'll end up with a final answer of minus 14th ln of 7 cos 2x plus c. Cool. Okay, one last trick to show you. So here are two things that we previously haven't had standard integration results for. They are actually in the formula book, so this thing I'm going to prove, you don't have to learn it. You might be asked to do the proof though. And we're going to integrate tan x. Now tan x is sine x over cos x is the key thing here. And if we think again about our fx here being cos x, what would the differential of that be? It would be minus sine x. So we're kind of nearly there. We just need the top of that to be a minus. So let's do that. We want this to be minus sine x over cos x. And the way we're going to adapt for the fact that we've got a minus sign added to it is we're going to put a minus sign at the front as well. So that minus and that minus will cancel out. Those are exactly the same things. I should be putting dx on these. And so we will go to minus ln and then of the bottom. So minus ln of cos x and then, yeah, plus c. So that's it. Tan x goes to minus ln of cos x plus c, and that's how we prove it. What about this second one? Have I made this a little bit more awkward? Maybe. Cot is 1 over tan, so it's going to be cos 3x over sine 3x. And then again, so we'll take our fx to be sine 3x. And if we differentiate that, we're going to go to 3 cos 3x. That's nearly what we've got. So we want the top to be 3 cos 3x, but we don't want to change its value. So we're going to need to put in a factor of a third there. And then we can stick that third at the front of our fraction. And then we've got something that matches up to our fx and our f dash x. So our final answer there would be a third times ln of sine 3x plus c. More generally, cot x integrates to just ln of sine x plus c, but we did a version there that had a bit of reverse chain rule in it as well. So yeah, that's all I've got for you.